So some of the stuff I'll present, they did while they were interns at FAIR. And then lots of other people contributed as well, but they're grown-ups, so they don't get pictures. So one on board, Sumit Chopra, Sumit Shantala, Rob Fergus, that's the name, and there's some more stuff. Okay, so the errors and opinions are mine. Okay, so basically what I'm going to talk about is, so I'm going to talk about structure in neural networks, and I'm going to say, well, what do you do if you have kind of weirdly structured inputs? And by weirdly structured inputs, basically I'm going to mean sets of things as opposed to fixed size vectors, and sets of things plus additional stuff. But before we get to that, we're going to say what's the kind of standard things. So there are neural networks that work pretty well now. So for some data types, you have really good so ComNets essentially are state-of-the-art on a lot of vision tasks. So for anything that is translation invariant and kind of has the correct scale, has the correct scaling structure, ComNets work well for. So they work well for speech. They work well for images. They work well for more generic audio. They work well for text, actually. Text is translation invariant. It kind of has this composable structure, but it's more complicated. Recurrent neural networks work really well for ordered sequential data. So, by the way, recurrent neural networks, like when I think of a recurrent neural network, I think of something that inputs a sequence and outputs a sequence. I mean, the word recurrent neural network just means any neural network with a cycle connection, so it's much more general. But the ones where you take an RNN and apply it to a sequence tends to work reasonably well. So the difference between, here we had grid structured and translation invariant. Actually, RNNs apply to sequences are translation invariant. But here you have sequential, you have a notion of order. And those things work. What doesn't work usually very well is fully connected feed-forward networks. So raise your hand if you know what a fully connected feed-forward network is. Okay, so most people have seen it. Okay, so let's start with that. So in some sense, the most classic, most basic neural network architecture is fully connected. And that is, you take as input a vector. So you input a vector. You pass it through a bunch of layers. Each layer is a kind of a simple thing. So you take your vector, you pass it through a bunch of layers. Each layer is form affine map, and then pointwise nonlinearity. And you just push this thing through this layer, and then you output a vector. And usually you optimize A and B via stochastic gradient. So let me actually say what. So we'll need some more of these. We'll need a little bit more kind of terminology and ideas later. So let me go through. So when I say given task usually means a choice of objective function, a choice of loss function in a data set. So task just means loss of data in this sense. And then if the outputs are supposed to be categorical, you need to do something, because the machine I described in the previous slide, well, this slide, you do a bunch of stuff and you get a vector after several layers of this. So if your output is categorical, you got to do something. The thing that you usually do is you take a softmax on the final output vector, and then you use negative log likelihood as loss. So standard feed-forward network for classification looks like bunch of affine layers, then the last affine layer you hit it with a softmax, and then your loss is just the coordinate corresponding to the, well, you need a log. So softmax and then log, and then your loss is just the, the value of the coordinate that should have been the correct answer. Okay, so the nice thing about that, by the way, is you can sample from it if you want. So when we talk about RNNs later, it will be useful to know that we can sample from the output of the network. But okay, so that is a fully connected feed-forward network. So the problem is that feed-forward networks, I mean, they're just not that great. They don't do anything especially well. So despite all the hoopla over deep learning in the past few years, if you have a problem, you can try to run, and if you have a problem that just has some, vector data that's unstructured in any other way, except that it happens to, your data happens to be vectors, probably you can do something better than a fully connected network. I mean, you can make them, they work, you can optimize them, they do something, but almost always you can do something better. So now this is just, the first part of this talk is kind of fluffy. I apologize. I mean, if you have to work on your NIPS paper, the first part is maybe the best place to do it. There's going to be a lot of opinions, and then it'll get a little less fluffy as it goes along. Anyway, so there's this tension. I mean, so when I was a grad student, I was in kind of the wavelet/applied math world, and there was the sense that deep learning was crazy because they weren't, the people who were doing deep learning were crazy because they weren't trying to understand anything. And you have things like wavelet transform, and you could say, well, I want to do wavelets. Why would I want to mess with learning all these things? And on the other hand, there's this other thing, which is, well, I actually want to learn all the things because I want my algorithm to be, I want it to be generic enough that given data that I have no idea what it is, I should be able to figure it out. I want one generic algorithm. And there's this tension between these two ideas of trying to say, okay, here's the actual structure that my problem has. I'm going to take that and use it as much as I can. And there's a tension between that and saying, no, I want to be very disciplined about allowing myself to use any structure from the data that the algorithm doesn't figure out for itself. And so there is tension, but they're not mutually exclusive. And so convolutional nets, I think, is a really good example of where kind of people figured out the right level of thing. So it's absolutely critical for the success of convolutional networks that they have the correct multi-scale structure, that they have the translation variance, that everything works out the way, for example, Stefan Locke talked about. It's also absolutely critical that you train end-to-end. And it was, I mean, there haven't been a lot of success stories in the same way, where you really, where people really, the structure really matched the problem, and people said, okay, we're going to train it end-to-end. It would be nice if there were more things like this. So let's talk about what a convolutional network is. Raise your hand if you know these things. Oh, pretty much everyone. Wow, that's more hands than went up for fully connected. So maybe, let's see, I don't know now. Okay, it's the same as a fully connected, except two things different. One, all the linear layers are convolutions. Convolutions are linear, but it's a special form of linear. And usually you have pooling operations. Actually, that's less in vogue now. People just do strided convolutions, but strided convolutions is, you can consider it a form of pooling. So this thing is, I guess, old-fashioned because it's now 2016, not 2014, but still, people do pooling. They just do pooling by subsampling. But basically, the two things you add, the things that you add, well, in some sense you subtract. So this thing is actually subtracting something from a fully connected network. You're saying, well, no, I'm not going to take any linear thing. I really want it to have a special structure. And the special structure is exactly the one that is invariant to translations. And then you have this other thing where you subsample over scales. Again, this is something very special to grids. You get invariance at the cost of low resolution. And so these things have worked, again, because the invariances and the symmetries of the model match the invariances and symmetries of the problems that people use them for. This is important. I mean, this is, again, it's super important that you do model fitting. It's super important that you learn all the way down to the pixels. But it's also super important the model has these properties. Okay, so last really opinion slide, and then it'll be slide less fluffy. So there's a lot of space. I mean, they asked us to do open problems at the end, and I'm kind of doing them here, and I'll do some at the very end as well. But so right now, there's kind of a huge opportunity for doing kind of work with ComNets, and that's because what we use for optimizing ComNets is plain SGD. That is really still the best thing. There are some, I mean, so people use batch norm now, so that's slightly less plain SGD, but it's still essentially same plain SGD. So the optimization technology is super primitive, and people haven't, I mean, up until recently, there were only a kind of small group of people working on ComNets, and so there wasn't a kind of big optimization community built around it. And in particular, there aren't a lot of optimization algorithms that really use the structure of the network. Actually, this is true for deep neural networks in general. People use generic optimization, and you have something that is broken into sequences of layers, and each layer is very simple. And in fact, we know a lot about kind of affine things. We know a lot about point-wise nonlinearities. And still, we just use plain SGD because we haven't figured out something better. But there's a lot of space out there. And batch norm is a great example. Batch norm makes a huge difference when you optimize, when you try and learn a ComNet with ReLUs. And it really actually is built around the structure of a ComNet with ReLUs because it uses the fact that, it fixes the fact that when you have a ComNet with ReLUs, the outputs at each layer are positive, which is terrible for gradients, and it gives you really badly scaled, really badly scaled ellipses. So it fixes that. And then you have things like, well, net-to-net is also a really kind of nice idea. It's a very natural idea that really uses the fact that you have a multi-scale network that you can kind of make it bigger and deeper as you go. So you can start with a very simple energy surface because you use a very small network, and then you kind of make your network bigger as the optimization proceeds. But more generally, people still aren't really using the structure of the network in their optimization algorithms, so there's a huge opportunity. And the same goes for the kind of theoretical analysis. So Stefan Millat and students, and notwithstanding, a lot of people, when they say, okay, I want to study, yes? Is it?
Yeah, it's not a geometry question. Do you really need to worry about optimization?
So
there's this nice paper from Andrew Ing where he showed you can actually get good results with random weights.
Well, okay, so if you try doing ImageNet with random weights, right, there's a huge difference. You can try it. It still does something. But
I just wanted to find out, there's a lot
right.
of
No. So I think it's a really good question, actually. So let me hold on. Let me get 2 bullets, and then I'll answer the question more. So the point is that so going back here, like you really don't want to do things like, well, okay, so a lot of times when I talk to people from math departments who have met me, and they say, oh, well, what I'm working on, and so on, and they say, well, okay, I'd like to get into that. They talk about, they look at kind of, they say, well, a natural problem would be to look at a really small neural network and completely understand all the local minima and the structure of the optima and so on and so forth. And I don't think that's a good idea because generic kind of fully connected neural networks don't work that well. It's not necessarily a good idea to understand them. And actually, you see a lot of papers like this where people really try and understand this thing. And so I don't think you should do that. You can if you want to. And I mean, I've been wrong about a lot of things before, and it's just my opinion. Like, it's not a thing. But I think it's better to use the fact that you know certain kinds of things, the structure of certain kinds of things have proved to be useful. And what you want to do is say, what is about the structure of those things that have proved to be useful, and how can I transfer them? To go back to your question, actually, I think the optimization we do now is complete shit. Like, we don't even know when. So if you ask somebody, did your optimization converge? The answer is, I don't know. We annealed because we lower the learning rate as we're going, right? So we don't actually know if it even converged. In fact, it didn't. We just annealed it to the point where it stopped decreasing, right? The optimization is really quite bad. And still, there's a huge difference. So if you look at kind of the network architectures from 5 or 6 years ago, you could get away with doing random weights. In fact, there was, Jan has a paper like this, Jan and Histins, or Kore Papapoulou, and who else is on that paper? I can't remember. But yeah, have the same sort of, so back in the Caltech 101 era, they said, okay, let's just try a network with random weights. And did just a little bit worse than if you trained end-to-end. And that was when networks were like 2 or 3 layers deep, right? And where there were a few, where the total number of training images was a few thousand. But if you try the same thing on ImageNet, it's a huge difference, right? If you try and just take a random, random initializations. In fact, even if you're very clever with the random initializations, you try and do DCT, whatever. Like, it's nowhere near as good. Like, it's just completely worse. So the really cool thing here is that even though we have crappy optimization, it's still doing something super useful, right? Even though what we're doing is not very good at all, it still is very important to getting the thing to work. So I think there's really a lot of these great open problems of why is it that when I take a ComNet, I can do kind of really bad optimization and still get a good result. Like, what is it about the structure, and how can I transfer that structure to other problems? Okay, so now we'll stop talking about ComNets, and we'll start talking about sequence-type networks. Okay, so sequential networks, we're not necessarily talking about RNNs yet. We're talking about things that a sequence comes in and a sequence goes out. So the thing doesn't have to be recurrent. But you see that there's a problem. If your output at a given time step is some function of all your previous inputs, you're going to have a problem as the number of inputs gets bigger and bigger and bigger and bigger, right? So you got to do something about that. So there's actually a lot of strategies, but here let's talk quickly about 2 strategies. One of them is just to say, well, I'm not going to go all the way back forever. I'll just have a fixed memory size, and I'll go back, this far, and everything else after that I'll ignore. So in some sense, you can think about a simple version of this is just taking a feed-forward network and just covering each of the slots and just sliding that along your time sequence. And then another strategy, which has proven to be somewhat better than this one, I think, is recurrence. And that one basically says, well, we'll say more about it. That is not supposed to be there anymore. Anyway, so start here. So again, we have input sequence x0, x1, xn, output sequence y0, y1. And so the recurrent trick is you have a hidden state sequence, and you update things like this. So the one part of the network updates the hidden state, and then the output is a function of the hidden state. Now, the trick here is that the hidden state at a time step is a function of the hidden state at a previous time step and the next input. And I've written this, but you could make it more complicated. You could put some number of x's, and you could put some number of x's and y's here, or whatever. I just wrote a reasonably simple version of it. So in ComNets, really we do linear, nonlinearity. Actually, for RNNs, for recurrent things, multiplicative interactions seem to be important. I don't think so. There are people who would fight me on this, but I don't think it's very well understood yet exactly what they do. But they do seem to make things better. So multiplicative interactions seem to be important for recurrent networks. Now, once you set up something like this, if you unroll that out, a recurrent network is as the length of the sequence. So it can be super deep, even though this thing is kind of a fixed parameter size. So recurrent networks, in some sense, have a lot of power per parameter compared to kind of the feed-forward fixed memory thing that we described in the previous slide. Okay, so now this is a recurrent network. So let's see, what time is it? Okay, so everything we've talked about up until now, yes?
Yeah, just a comment here on between the ComNet and the recurrent networks.
Yep.
But do you see that there's also this sort of hybrid in between where you would just have a ComNet over the sequence that is defined as an IIR sequence?
Yeah. So
Are
so I don't know if am I allowed to. So Mark Tiger, you know Mark. He actually did a bunch of things like this, and
okay.
so yeah. So there are things. In fact, okay. So the first thing is.
What was the question?
And we're-
Yeah, so the question was, can you imagine some sort of hybrid? Because if you imagine that there was no nonlinearity here, just for simplicity. So I've written this f. Imagine this f had no nonlinearity. You can imagine just iterating this out, and what you get is actually a convolutional network. Except it's a convolution that isn't, the filter size isn't finite. It's infinitely long in one direction and exponentially decaying, right? So if you kind of choose f and g correctly, a recurrent network is a CONNET. Actually, a recurrent network is always a CONNET in the sense that it's convolutionally, it's translation invariant, but it is particularly the same kind of CONNET as we showed before, with a filter that stretches back forever if, your f has a certain form. And for example, Mark Tiger at FAIR has been working on these things. So there is, there's good reasons to work on them like that, in the sense that, for example, the stuff that Mark talks about in terms of theory of why CONNET works, and what Stefan talks about the theory of why CONNETs work, that actually should kind of go through to that setting, right? But okay, so, okay, so everything we talked about now eats arrays of some form, right? So I'm going to kind of take an aside. Like I apologize. Like I wanted to introduce some standard architectures, and we're gonna see them over and over again. But one aside I have to make is we have things that are eating vectors or arrays or things like that, and the data you get isn't always presented as a vector or array or anything like that. So, for example, recurrent networks are often applied to language, and language, if you look at it at the word level, is a sequence of tokens. It's not a sequence of vectors. So what do you do? So this is your duty as a practitioner. Still, there's no generic way of someone gives you data that looks like blah, and now it comes and gets turned into a vector for you. You always have to do something. If your data came as a vector, okay, it comes as a vector. You probably want to whiten it or do some stuff anyway. But if it didn't come as a vector, if it just came as some sequence of tokens or something like that, or whatever it came as, you have to, if you want to use those tools, you have to get it into the format of arrays. And so we'll start with one really simple example. We'll see some more later. But probably the most standard way of getting a finite set of objects into array form is a lookup table. And a lookup table, well, you can think of it as a really big linear. So basically, if you have, if your inputs are all elements of a finite set, and the finite set has size n, you just make a big n by d matrix. And then when you get the input, you just output the row of that matrix corresponding to the input, and that's called lookup table. And in literature, and definitely where I'm from, we call that an embedding for the word, or a word embedding. And that's like that's super standard. Like you see it all over the place. And again, that's equivalent to just taking. That's equivalent to having a giant linear layer and sparse inputs with a kind of one-hot representation. One exactly where that word is and zeros everywhere else. And usually train the word embeddings along with models. And this is an important thing. The word embeddings usually have more parameters than the rest of the model. So if you look at kind of RNNs that are trained at the word level, the embeddings take up all the parameters. The embeddings are huge compared to the rest of the model. So there's a lot of power in the word embeddings. Okay, so now that we've seen that, let's see an example of a recurrent language model. So this is kind of a recurrent neural network, but specialized to the setting where the input sequence is a sequence of words, and the output sequence is a sequence of words, and actually the output sequence is just the input sequence shifted by 1. In other words, given an input sequence of W0, W1, W2, up to Wm, your goal is to predict Wm plus 1, right? So here, this is the input. This output. Oh, I didn't write that. That's terrible. I apologize. So the goal here is xn. Oh, yes, I did write it. Okay, sorry. So the input is the embedding of the kind of nth word. That's the nth input embedding, and the output that you're supposed to match is the n plus 1. But you got to see the sequence all the way up to the nth one. So the network updates exactly as before. Again, I haven't specified what f and g are. And then, as we said a few slides back, you can take a softmax over the kind of output to sample over y hat. Let's see what this looks like in images. Okay, so the thing about a recurrent language model is it can feed itself, right? So let's look at this. Let's look at this equation one more time. You have this input. You get a y hat, which is g of hi, and then if you had a softmax, you can sample that y hat. So after you've trained this thing, so you had this very long. You had this big text document, and you kept eating the words and trying to predict the next one, and now you don't have a text document anymore, you just have your model. You can still kind of generate words because you can start with some seed sequence, then you get the hidden state, you get some yi, you sample from it, and you just put that at the end of your sequence and keep going, and you can feed your own sequence, feed your own model this way. So it looks like this. You start with something, whatever it was, you start with some, wow, can you read that? Oh, that's really, okay, so this says encoder embedding, this says state, this says decoder embedding, this says sample. So you start with some input, and presumably you've seen a bunch of other inputs, so you've gotten to get a good state going. You feed this into your encoder embedding, you update your state, you throw it through the decoder embedding, you sample, that gives you the next one. And guess what? You can toss this back into the machine, right? And so if you look, so for example, there's lots of these, yes?
So it's t plus 1 on top is the estimation, or is the next?
It's the sampling. Okay, so let me say the process one more time. I apologize if it's, well, it's hard to read and I'm confusing anyway. So again, the way we trained this thing was that the thing that you're trying to output is the previous sample, right? So if you've seen x1 up to xt, you train the thing to output xt plus 1, right? And so what we're going to do now, exactly as I showed in the kind of third or fourth slide, when I say predict xt plus 1, we do that with a softmax over the outputs, right? And what we're doing here is we predict something, and then we sample over that softmax, right? So we have a probability distribution over all the words, and we get a sample. And that sample, we're going to take it to be the next element in the sequence, and we'll feed it back in. Is it okay?
Okay, so, and at some point we compare it with the real next.
Oh, okay, sorry. No, this was just for fun after we've trained our model. I'm just saying you could actually generate new things like this. So when you're training it, one standard, there's lots of ways of training these things, but the most standard way of training these things is you just take the next word in the sequence. So you have x1 up to xt, and now you have xt plus 1, and you can use the log softmax just like before, and you just compare, you just say, I want the log likelihood of the next word in the sequence to be as high as possible. Okay? So training time is completely different. I'm saying that we could actually, at test time, just generate it from scratch. The reason why I'm going through this, eventually I'm going to talk about memory networks, and I want to show the same picture in the way a memory network looks. So I'm going through here. So what this is, once you've trained it, what this is a random walk with memory, right? So you start at some point in your space, so all these dots, sorry, I'm putting it on my screen, you can't see my screen, so I'll point it here. All these dots are words in your dictionary, right? And say you start at some word, you're going to do a random walk, right? So after so this is your xt, you get what you think the next thing is, so you get some probability distribution over the words, right, for your output. This is here, and then you can sample from that. Boom, you end up here, and you can keep repeating. You can feed that one into your thing. You get a new probability distribution over words. You feed that as the next step. You update your hidden state, so on and so forth, and you continue like this. And you have a random walk over the words, which is super cool. So if you literally had a Markovian, if you said, I want a real random walk, that just depends on where I am, that's a bigram model, right? So bigram model means you count, you say, what's the probability of any pair of words? And you just count those, and you normalize your distribution that way. So if you really wanted a Markovian, a real random walk, then you would have a bigram model. Here, this is not a bigram model, it's an RNN, so it has a history. It's not Markovian. After n steps, where you're going to jump to depends on all that history, right? But it's a random walk that's not Markovian. Okay, so let's see, what time is it? It is now 12. Okay, so we'll take 10 more minutes and then we'll take a break. So okay, so that was the kind of first little chunk of the thing where we're going to talk about kind of the classical structure. So the kind of standard structures that are working are comnets and recurrent nets. Fully connected things don't really work. There's a bunch of other weird things like, well, not weird, actually, they're pretty cool. So there's things like recursive networks, where you kind of combine certain ideas that are, I mean, I wouldn't say that they're working super well yet, but they're super interesting. There's a bunch of other kind of well-structured neural networks that are interesting, but we'll just keep those two comnets and RNNs as examples of things that are super structured. And now I'm going to say, okay, so I told you that the structure is super important. You really care about it, and you should have networks that respect it. So now I'm going to say, so as I said in the beginning of my talk, I'm going to talk about how do you deal with inputs that are sets, that don't have, I mean, they're not even a sequence, they're not a grid, none of those, you just have a set. So I told you the structure is important, so why do you want to input a set of vectors? It's terrible, it has no structure at all. I mean, that's the worst thing. So actually sets, just by themselves, do have some structure. They have permutation and variance, and that actually matters. So I'll show you, probably not today, but tomorrow or the day after, I'll show you one thing that we've been trying is we want to play a video game. So we want to have a bunch of little guys fight a bunch of other little guys in a video game, and we want a controller that controls all the guys. And it doesn't matter whether it's agent 1, agent 2, agent 3, or agent 3, agent 2, agent 1. The order doesn't matter, right? And it's actually important that your neural network respects that. And actually, it doesn't matter how many there are, or how few there are. You want your network to kind of be okay with that. So that's actually that is a kind of invariance in your data, and sometimes you need to deal with that. Permutation variance is actually a thing. The second reason why you really want to input sets is you have a sparse representation. So there's lots of times, if you know, like, how would you write a sparse matrix? Well, there's lots of different formats, but roughly you say where the non-zeros are, right? And where the non-zeros are is going to be a set. It's not going to be a nice vector. It's not going to be a fixed length representation. There's lots of times where you have input that is in some sense sparse, and you need to use that, or you want to use it because of computational limits or whatever. Like, even if it came from something that was well structured, dealing with the full structure is annoying. You want to deal with the sparse version, so it'd be nice to eat a set that has that sparse representation. Then there's a third reason, which I think currently is, actually these two are important, but this one we use quite a bit. You actually have some structure in mind, but you don't want to decide it at the moment you're building your architecture. You want that structure to matter at test time. So you want to be able to have a network that eats some vectors or eats some stuff so that eats kind of a set of vectors and some information about the structure of those vectors, and then outputs something. And the structure is determined at runtime rather than at train time. This is another reason why you want to have input sets. So I wrote input sets, but here you want to be able to input sets plus structure. And we'll talk about things that do that. And then here's a last reason why you might want to input sets. I think this is kind of a bad reason. Probably you should change it. But sometimes you say, well, you have no choice because that's how the enemy gave me my data. Well, you always have a choice. But so if none of these things, or you can't think of another good reason, maybe you can think of something else. Yes?
Just a clarification. So make the dimensional structure at runtime or clinical time?
Crop. So runtime.
Okay.
So input run, not train. So, not as opposed to building your architecture. So that should be runtime. That is much clearer that way. Sorry. Yes. Okay. So let me show one example, or I'll show. So let me give you some examples of where you have kind of sets as inputs, and then we'll take a break. So I'll say these two, and I'll show this one. So and one example of. So, for example, a lot of people are now trying to use comnets for describing shapes. You have a library of scanned shapes. You want to So that the input is a point cloud. Actually, it's super annoying to deal with that point cloud as a parameterized object. It'd be really nice to just you eat the set of points and you output some vector, right? So this is an example where the 3D the set of points actually has really nice structure to it. It is points that lie on a surface because again you scan this with Connect or something like that, and you have this database of objects, and I want to classify things as belonging to one of those objects or look it up, like do nearest neighbors to find it, or maybe I want to be able to take my phone and move around something and then look it up in a store or whatever. But the point is those points actually have really nice structure because they live on a object in space. So all the nice kind of manifold properties are there, all the kind of multi-scale properties are there, but every one of those shapes is different. So you can't just have one multi-scale structure or one manifold structure. You need to be able to input that at runtime, right? So this is an example where it'd be nice to be able to have kind of architectures that include sets and structure. So a second kind of generic thing is when you have multimodal data. In other words, someone gives you things that it's text and images and maybe audio too, and you need to find some way of combining all these things. It's useful if you can kind of put all those different modalities into a set and just think to yourself. Let me show you a third thing and then we'll take a break. So one thing we've been playing with a lot is these games. Oh wait, let's not. Okay, so these are little games. Let me start from the beginning again. Okay, so we have this little agent, and it wanders around a maze, and it has to go to the goal. So this one, it has to, by luck, so sometimes it's on the other side, so it has to push the block away, right? And it has to then figure out how to get to the goal, and it does it. What it sees is this. So it doesn't see this in this particular version. It sees just a bunch of text describing the thing. And the reason it sees a bunch of text describing the thing is that's a super sparse description of this environment. Rather than having ComNet eat this, which you could, we also tried it with ComNet, but it actually doesn't work as well. The problem is that there's very few blocks compared to the number of things. So actually, it's very nice to be able to eat a set here because then it's actually a sparse representation of the board, and you can get something from that. So I'll talk more about these games later, but I just want to show an example of something where you kind of have inputs that look like this. It's just a set of things. This set is variable length. In fact, it's a set of sets. Each of these is variable length. And it's the reason why we want, why that's kind of necessary is otherwise you have to have lots of, well, this one is pretty dense, but a lot of these are essentially mostly empty. Okay, so let's pause for a couple, like 10 minutes and come back.